We're going to be concerned with the idea of limit and up. A approaches A. All right, will be an L. And the idea behind this, x gets close to a particular function is to get close. So, of the idea of limits, function f of x is x approach L. X approach A, f of x, L, or exactly later. For the meanwhile, of what this means. That's of x and a number in the x-axis. We don't concern ourselves with does at the be defined at the point A. Defined, however, in an A, but not necessarily. And we say that the limit of the function is a number L. You can think of this as being a value on the y-axis. Whenever you take to A, close to L. So the value is here, the resulting value to L. And what's really, if we want to stay, what we need to do to achieve that is, let's look at the y equals x. Here's perhaps 1. Let's look at the numbers. Now we don't concern ourselves with what 2, but we're interested in an approximation of the split and square it. So that, for example, if 4, since it's very close, it's going to be close to this. It's very close to the square root of 2. Likewise, with 1, any number in between them. Oh, and this too large in between. A number closer, you'd expect that what we would need to do would be to pick up to the square root of 2. Here, in this case, here, 2 is the function at the square. When that's the case, when the function is the point continuous, and obviously later. This will also later. Namely, if you want to state an L, you have to be able to close A, the resulting values of f of x distance away from L. So roughly, as x approaches A is a number. Right? It's that number so that x close to A, then precise definition of the limit approaches of f of x and x of A is equal to f. And now the Greek letters epsilon are used, usually small numbers, although it's generally intended as so provide for every number epsilon there number delta greater that x minus L epsilon when want 0 and x minus A. So, explain here. First of all, the limit is a number, and this number, if you line close to L, which is the absolute value of the distance from f of x to L, epsilon close to L, delta close, but the 0 x is never to A, 0 is to A, so that x is not. Is a definition that should be, in which you can think. It's really easy, but is not memorized. It should be remembered. The ones which are located require. All right, let's look at. If here's a number A, then we do not concern ourselves as does not need to be defined. We say that the function, given any epsilon greater than A between L and L minus epsilon, if we wish to, between L plus epsilon, how small epsilon is, and a delta back over x between A minus A plus delta, size of f of x, well, minus epsilon, and with a large epsilon here, but no matter how small epsilon, to be perhaps a smaller, so that's between L minus, say the distance is less than epsilon, is x lie between s delta and A plus delta. Frequently, the limit L actually be at A. The function f is said to be considered. Here's the definition of the I'm going to put down here the definition is continuous at A as x of f of A. This actually, 1 at A, it has, at least in a small interval, in order for the limit, and the limit will the value of the function. Okay, and I think we take care of it to talk about one, which is A, is written with a limit with a plus above the A, f of x, if for each epsilon there is a delta, so that it's between f of x and epsilon, where the x minus A. Here note that and the fact that A says that x is large, only consider those x's from A, and if L, as close as you'd like, when x is close to it from the right-hand side of f, is that the left-hand side is done similarly. As x from the left is equal if 0, there is 0, so that x minus L epsilon less than A minus is less than delta. So no absolute values here, but A, that's the left side of A, have got to be able to stay desired. Epsilon close, providing we stay on the left, delta close, in delta is a function. And in order to show that the definition doesn't ever show that it equals L, I've got to be able to tell same thing is true here. That if the limit as x approaches A does in the limit from the right, and they're the same number, convert from the right exists and equals L, A exists and equals L. If the limit from the left exists and 1 delta, so that f of x on the left-hand side, f of x minus L is less than on the right-hand side. If you take the smaller of those two, x minus L will be either side, and that's since that old, no matter how small such delta will be found, and the smaller with the delta for that given f. We'll look in a moment examples of how we really don't want to do that. Sorry. It's really nice for when, so that A of the function, and also to have some limits of combination. We want to look at now of how to find one for a given function. And the function, this may be a daisy one, on different things that are needed to find an epsilon, for example. Let's consider f of x is equal to 3. Equation of a line, and 0y is minus 3, so it goes up at 1, it's this one, and at 2, and it's an equation of a line, fashion like so. And 2 of x. You expect that as x approaches the 1. So we have a reason for it here, and now what was the case? Epsilon greater than 0, and greater than 0, so x minus f and epsilon, 0 is less, A is less. That's to say, here is 2x, L to 1. So we want, so that this is less than, 0 is less than, f2, approaching is less than delta. Okay. But this quantity 2x minus value. So we want 1 when 0 is less than delta. This is 2 times f minus 2. We want that. That's to say we want f to be less than f2. Well, 2 is less than epsilon over. And this is going to happen, and this will show that the limit is 1. Do here is to let delta. We've now found that if absolute net delta, epsilon, 2 times it is less than epsilon, absolute 2x minus 3 minus 1 epsilon. You can visualize this picture situation. If we want to minus epsilon and line with slope 2, say back in 2 minus and 2 epsilon over 2. I'm going to have to stay that in order to get that function 2x minus the epsilon close to a nice simple case here. This is a straight line. More complicated. What we really want in the long run, rules that will allow us delta if possible, with epsilon and delta when it's needed. So here's an example of find a given delta for this particular function. Okay, let's consider issues 3, constant 2. Well, going to be equal to 2. Now this is a little simpler, a little funny here. The function, which is 2, to show than 0, define delta greater than that. Absolute f of x minus L is, right? What is less than absolute x is less than delta. Here f of x is 2 and L is 2. So we want less than epsilon, 2 is equal to 0. So what this says is that any, right? If I wanted 2 minus epsilon, however here, near 3, stay near that. In fact, here could have been at the been any constant function. The limit of a constant instance. Argument holds here is that given any epsilon should take for delta case, because usually delta that you need depends very heavily on. At any rate, this form that the limit constant function is. We want to consider equals mx. Right? So, and we want general at a point A to show that the limit as x approaches mx plus b equals to ma plus b. That the value of the function at the point. So that if you stay close, the result will be a. Now epsilon greater than 0. Greater than 0. So f of x b. Limit epsilon when absolute x minus a. This is b minus b is 0 minus a. So this is absolute x minus to be less than epsilon. Now if n, we already know that which is constant, and we is but which would if m was 0. So is the case where it's 0. And we want epsilon. Well, we can do epsilon when absolute x less than epsilon divided m. That is the delta that you should. And x minus a less than that delta, x minus a will be less than epsilon, which is what was 0 was less than x delta. This formula holding approaches a of mx plus b. That's to say mx plus b. The limit as you approach a number x plus b point. But in general, on its domain, if that domain, the function here is an example of is the constant function. Okay. Now let's look at some involving epsilon. Right. The function squared. And as x approaches 2. And this is going to be the number. We want to see how to show that in deltas. Greater than 0. Greater than 0. Squared minus 4. What limit value? When 0 x minus 2 is. Alright. Control how close. And we want to how x, of course, x squared is. Take a look at this. This is absolute x plus 2. We want that. What's going to happen here? Well, this small and large, we should be in business. Suppose that we don't allow than 1. Be less than 1. Consider numbers that go up in 1 and 3. What happens to absolute x? Well, x is between 1 and 3, and x plus 2, 3, and so that x is no less. So that absolute x plus 2, absolute x minus less than or equal absolute x plus, keep this less than epsilon. That's to say if, absolute x minus, if we keep that 2 less than 5. Now, to delta, we also, our delta status below, that's to say we really went to the minimum of 1 over 5. It's which is smaller, if that's delta. This will happen right here. 5 will be larger than 2. Absolute x minus 2 will be less. Absolute x less than epsilon. And as a consequence, when x quantity delta, and relatively tricky, but relatively tricky, epsilon. Notice that whenever you do find just one delta, it will do. Perhaps even a larger. If you find a given delta, that will do for that epsilon. F of x equals square. So here, and let's look at the score. If the answer would be 2, x approaches 4. To say we want to show that x approaches 4, the square root of x equal to 2. Perhaps x approaches 3 would be. Let's do that. Let's change this. And then you'd expect, in general, say that the limit of x approach should be the square root of a. Square root function is continuous. Okay, but let's, for example, here's the function, the number a, and here. So what do we need to do? Show that given epsilon, we can always find, so that square root minus square root less than epsilon, 0 is than absolute x is less than delta. Find the delta. Well, what is this? Square root x like is absolute x minus 3. What I want to do here is multiply by square root x to square root of 3 in absolute value and divide root x. This is, I'm in general going so small that we'd stay within the function square root of x. It's just the delta. If we do that, what we want to do here is x3, Roger, absolute square root x3 less. And do this providing this is small, this is where we wish, any delta we wish to equal epsilon, too large. However, 3, right? So it's square root x plus larger is 3. It doesn't get any, quotient is not going to get too large. What? Here, absolute minus 3 divided epsilon, then epsilon and our square root x minus epsilon. That's the safe case, be equal as long as it's less. So if we let delta, epsilon, and 3, we will be in good shape. And absolute 3 will be less than epsilon. Follow that epsilon is square root of 3, providing x is, providing 3 epsilon, that x is within epsilon of 3. Epsilon. To stay within epsilon, the root of 3. And that's because to stay in this interval here, this being the square root of close to 3. To do over here like so. Have the function value stay close. Happens to with a function, and we look at the general limit, where a is, we're going to need a couple of things. Everyone knows that squared factors into plus b. A cubed minus b and a to the n minus b to the n, right, can be being one of the factors. The remaining factor is a to the n minus plus a to the n minus plus a minus 3 times plus, and this continues last term, which is b to the. As x approaches root, we want to claim the root of a. That the nth root of x is. We want to do this for 0. And that a is equal to 0, tries to show that the limit is nth root of x is the 0. Now, to be even, this only makes a 0 from the right. Odd, it makes sense from these. It's easy to show that. Also, if n is shown this, its relative x approaches a, an odd root, which is the corresponding odd. This. What do we need to do? N greater than 0, we need to find. So that absolute of x minus epsilon when 0 is less than f is less than delta. And this is we want and divide. That you get if you let this be up above. Right? If we let this be, there's a by this b, a to the n minus 1, the n minus 1, that's by the n minus 1 plus the n of x to the n root of plus terms here, and finally a 1. Divide by this also. We want this to be less. We want to find a delta so that it will divide by of x to the n plus and so to the nth root n minus 1. When we multiply a minus b, the corresponding term over here, n minus 1 plus here, we are going to get s b to the n. And the numerator here, minus a, divided by this of x to the n plus the a to the n minus 1 in absolute value. This to be less than epsilon. Well, less than what we would get. Dividing x minus a by this, divide by the single quantity to say this is a divided of less than epsilon. We'll then have this less than epsilon. Keep insisting that absolute is less than nth root of 1 power. This is delta is also going to that less than a hand side of 0. Always insist here that delta b is the minimum of quantity right here. When that's the case, when f delta, then it is less. We work our way backwards and it's less than epsilon, and so this is less. That's what was required in the first. So this then the nth root as nth root of x approaches, and that the nth root for all at a 0. We now want to take a look at a function f a, and we want to look at the f. And the next is the limit of a constant times the limit. To say, as x approaches a of f of x is equal and is a real number, show then that then limit approaches a times f is c times a. The first thing to note here is not equal to 0. So that we've already, that is the limit, which is a, is equal to 0. If 0 times 0 and 0 times, so we can equal to 0. That's delta. So for we wish to find delta. When we do this, we'll be done with this type of a problem. When a function, we will always be able to evaluate the limit of the function. To remember this, the limit of a constant approaches a is constant times f. So for what we need to do, epsilon greater than 0, we need to f f of times f of a less than epsilon 0 x minus a. But that's to say that here we're working with times absolute f of a. L minus L less than epsilon. L is less than epsilon. Constant times f of x minus L less than epsilon, or f of minus L and epsilon over constant absolute value. Now what? X approaches L as x. So what we do is find the on epsilon c. Or find that delta. What? If 0 delta would be our delta here. If 0 is less than absolute x minus, then f of x minus 1 over absolute c times f less than epsilon. Cf of x and epsilon, and Cf for its limit. Right? Up here is that if f of a have that the limits of f of x is, or f of x and cf of x continuous at a. X approaches x will be cf continuous at a point and a constant continuous at a. And sometimes the function is the limit of the function. Sum of two functions. X approach of f of x to L, the limit as x of g to m. We want to conclude the limit as x approaches a of f of x is L plus M. Or if you like, approaches A of F is L plus M. To see this, given epsilon greater than G, so f of x plus G of x minus L plus M is less than epsilon when x minus A is less than. But what? You can rewrite this as f of x minus m. Absolute value, we want to keep that. Well, this less what we would get if we put n like so. That's the f of x, g of x, in absolute value or equals the triangle inequality. That's the inequality that a plus b are equal to absolute a absolute b. Sure. That's the epsilon. We would then have to be done. We could find the delta. Here we have things we can control close to L. To consider 1/2 of epsilon close to L by epsilon over 2, and if x close to m. Delta, a first delta, that's L in absolute value over 2 when 0 is less than that first delta. Here, just the as x approaches L, so we can find over 2. We can find the second delta, so that absolute minus m less than another half of delta, than absolute x minus the second delta. Be the smaller of, of delta 1 and delta 2. If it is, f of x minus g of x minus m will be less. This, and that's consequently, this will be when 0 absolute x minus a have the fact that the limit t of x is L plus, right? Which is memorable, the limits. Here is that if f of x is f of a continuous and this limit is g plus g is continuous, and the f of a plus the sum of two functions is again a continuous function. Products of that product, and considerably more tricky than the limit of difference of two functions. If you a rectangle A by B, could imagine a field perhaps. If instead of it being A by bit in the A direction, off by 3, come the amount off by 8, off by the two amounts that you measured it, 100 foot, 300 foot field, and if you're off your foot, you get extra 150 feet. 300 square foot area will be off by. The product small, be able to be small and be small. And in order, we want the following: if A is equal to F, and delta greater than 0, absolute does not get to be less when we look at x, absolute x minus the delta. We can choose f plus 1 if you want, f plus any number. Well, given epsilon, great epsilon equal to 1, given any epsilon greater than delta, greater than 0, absolute x minus a, then absolute f minus L epsilon. That will be less than epsilon minus epsilon. F of x will be between epsilon through out here minus epsilon. Which consequence of x absolute L plus epsilon. Very easily by considering 1 if L f of x absolute L plus absolute L minus epsilon, and so consequently be greater absolute f plus epsilon. If L of x is between epsilon, absolute f of x is less than negative, and also absolute f of x will be less than epsilon. be less than L minus epsilon, L plus epsilon, psi will be less than absolute. So that if the limit of x approaches a, bounded by some number n, that's to say for x than 0 and less than too large, we're going to need the limit of the product of the two limits when it exists. Now we're ready to factor the two limits. If the limit, say, is L, the limit as x of g of x m as x approach of f times g of x is, as shown, given epsilon, find the delta. Then 0. When 0x minus a delta, then g of x times m an epsilon. All right. Here is point complicated, and in order to get to is to add and subtract this absolute value. Rewrite this as absolute times g of x minus L g of x L minus L times, I want to keep that less than epsilon. Well, here I have x and have f of, and in fact here I can factor out L and m. That less than epsilon in absolute, but here is two sums. This less than epsilon will be less than epsilon. The g of x times f of x minus absolute times absolute f of x minus. This is absolute x minus m for quantities here. And quantity small because f, we're able to keep this quantity small, m, so that if this, and this to keep the whole thing small. Call this, since g of x approaches much, this, so this is no larger plus 1, larger than absolute L. This is going to be less than times x minus L plus absolute L times minus m. If we can keep this less than m, be done, because then this will. Okay, what we're going to do is we're going to take our two parts. We're going to keep on over times 2. So that the whole absolute m plus times m plus 1 times 2. So what we do is we find, so that f of x minus L is plus 1 times 1. We use the definition that of the limit f of x is L, t that we keep f up to L. And so g of x minus n is less than epsilon absolute times 2. The reason for the event that L is equal to 0 be 0. And this delta is again approaches m. Now if we take the minimum, then f of x minus L will be, x minus m will be less than this, plus this times this epsilon, plus another half of epsilon, and that's what this is going to be less than epsilon when 0 is less than absolute, is less than of delta 2. Limit of the product of the limits. That f is continuous as f of a, and g, m is g, f times g is at a. This functions at a point is, and also, in general, is a continuous. The quotient of two functions, also because if we numbers a and b close to 0, which is not defined, but if b is 0, then very c can affect the quotient a divided. I want to have some sort of statement as could be like this. If limit as x approaches of g of x m is greater than 0, so that is larger than half in absolute. Here is not equal to 0. G of x will be larger than this value when 0 is x minus a is less than up to a, then g absolute m over 2. So that it can't get, also we would have this problem of two numbers with a denominator I. Absolute m 2. Then, greater than that, 0 minus a less gives g of x m is less than epsilon. Absolute m. That's to say, g of x minus in absolute m 2 is absolute m over minus m is. And here we get that the g of is large m minus absolute m. Let's see that m is positive, larger than, of course, m over 2. All right, and the event has to say that m is negative. G of x is less than, adding plus absolute, that m is negative is absolute m over is less than with m over 2 will be over 2. And each of that, g of x larger than absolute m over than absolute x minus a. M. Consequence is that g of x approaches m cannot get to be arbitrary, so that if we're looking at dividing, it's not going to get arbitrarily as x approaches a. It's bounded away from 0, that fact. Right, we now want to look at the limit of the, and provided that the limit is not 0, quotient of the limits. Suppose that the limit approaches a equal to L. The limit as x approaches of g of x is equal to m 0. That the limit as x approaches of f over at x L divided by m, where x over g of x, of course. I'm going to show this directly. Is this, that the limit a of 1 over m. Then since x is the product 1 over g of x, product of the limit, the limit as x approaches is L divided by a. Okay, we need to show this. So given we need to find the delta. So that of x minus 1 over an absolute value when 0 is less than absolute less than delta. Say 0 less than x minus a implies that this is less than epsilon. 2. Putting this over a common denominator, g of x value, we can put the absolute denominator, which of course absolute g minus m. That's g of x, absolute m minus m. 1 over absolute g of x, absolute m. We want to keep, and we can do this, m, we can keep this small, too large, and this is, recall that we can find a delta, so no less than absolute x, less than that delta, but this is going to be less than g of x minus 1 over absolute g of x will be absolute m divided absolute 1 over absolute m. So if we can keep have this small, but what is this? This is we can keep epsilon absolute m squared over 2, and m squared over 2 no more than 1 over more than 1 times squared. This is no more than m over square, over more than 1 over epsilon. The whole thing will be less than epsilon. We keep this less than epsilon over 2. Be done, but we can find this. So absolute x minus second delta says that this is the second delta is just the for this number m squared over 2. G of x approaches m is. If we find the second delta, this is less than what? So we simply delta of these two. The array this will be less than epsilon, and consequently this will be less than epsilon. And given epsilon we have found and natural quotient of two functions. In addition, f happens to be continuous at A, then f of x is g of x is g of A divided by g of A. Quotient of two is also continuous. Continuous functions is a I wish to consider the limit of constants, and the reason this, if that which is a of x is equal to x, and f of x approaches a of g of x will be f. The continuity of f at m, and this means that as m is f continuity, an epsilon greater than 0. So that what? X might be less than epsilon when 0 is less, a is less than delta. Think of g of x as, given this epsilon, there is a delta, so that 0 is minus m and delta 1, that f of y, what's the limit, is less than 1, greater than 0. When 0 is less than m delta 1, then minus f of m is less than value. But this condition over here, because what? Equal to m, then we have m is less than epsilon. That is less than delta 1. When m is less than delta 1, y possibly equal to minus f of m is less than epsilon. Now we're going to use this epsilon. Even delta 1, so that the absolute x minus 2 implies m, absolute value, is our delta. Delta because what is less than delta when the f of g of x minus the absolute value is less than ever this occurs. So here's delta minus a, an absolute value, an absolute f of g of x less than epsilon. The end of a composition is what, and in the case continuous, then, and this says that the composition has as its limit, f, the limit is f of g of, it says that the limit of the composition is, the functions are continuous at a and at g of a. A number of functions which we could, we know that the limit approaches a equal to a as of a constant, right, to get it here, immediately gives us, along with constant times a function, the product of the limit, which is a of mx plus b, ma separately, but approaches a of mx plus b of mx plus the limit is x. Mx approaches as x approaches a of a, and b approaches b, as of ax plus c, a squared plus the limit of the sum. Each of these limits separately. The limit of a constant times a function, the limit of a function. Bx approaches b times x squared, b times x, the limit, so it's a times indeed. X approaches a, is a to the n. That's clearly, you could continue cubed, is x times, limit is x approaches a of a times a squared in general, like so. And better than Romeo, let's say b1 x plus squared, plus, and this could x to the n, as x, it's going to be equal to plus b1a to a squared with b and a to the limit of the sum is the product in each case, and is x to the n here, huh? That's similarly here, for polynomials are continuous. For rational, the limit x approaches a P over Q of x, where P is a polynomial, is going to be P of A provided not zero. Functions. Now we also know that the is continuous for A larger than 0. We've got limits to evaluate these facts. To evaluate example. As x approaches let's 2x minus equals to 6 minus 7, or this is 87 minus 7. Limit as x approaches square root of 3x, well, the square root function, so that means we can find the limit of 3x plus 7, 6t, and this is the square root of 13 function at the limit of 3x plus limit, and 4, x squared plus 3x sine. Right? The denominator does not approaches 3, or approaches 16.3, and so the answer is 3 over 3. The case, or one of the cases that's in will turn out to be very important. Here, the quotient approaches 0, which is 0. Then that you have two polynomials, then we know that looking at as the polynomial and the numerator approaches 0, then x minus a will also divide the denominator. This can frequently be used. Example, the limit is x of let's say x is x approaches 2 is 4 over x squared plus 3 so that it's 0. And 6 is 10 minus, well, we get a 0 in the denominator, and this 2 divides the numerator. So this is the limit as x minus 2 times x, and the denominator has minus 2 also. Consequently, this goes x plus 5, x squared, 5x is 3x, and now we're looking at this limit. As x approaches, consider the possibility that x, so that 2, this function is we would get if we canceled x from numerator and denominator. What we want now is two functions are equal except a, the limit as x approaches 8, obvious, I guess. X approaches 2, 4, the denominator, this function here, 9. So we have got a number of functions. When you've got one of those, you can find evaluating the function at the point, and continuous, you can breakly so that or functions which are of 1, except that the point is continuous, then you can by a into the function. We want one result that's, and is useful when the limits are not easy to find, will be used later. Sometimes it's called the pinching. The picture for this theorem is, suppose we've got a function f of x. Right? It may be different as x approaches a of f of x. Find a function g of x which is less than f, and another x which is greater, and both limit as x approaches a, essentially pinched, and it's to have as approaches a of g, which is the limit of h. Anyway, suppose the f of x is less x, an interval containing a minus delta t. Not necessarily at a. Move the possibility of a. They don't have to be defined. A of g is equals to L, equal to the limit approaches a of, and as x approaches f of x is L. An epsilon greater than 0. I always have to come back to epsilon doing with something new. Delta. First delta, so that 0x minus a less than implies, right, that x less than, right? And there's a second, so that less than absolute x minus delta, and the h of x is less than epsilon. Smaller of these two. G of x minus L is between f minus epsilon. H of x is between epsilon. We wanted this L is between epsilon, and this is the statement and L minus epsilon. Statement that H is between L and L minus epsilon. What? L minus less than G of x. We know G of x, which is less than L. Well, consequently, f of minus epsilon and L plus a, f of x minus L, so on. And was arbitrary, so f less than epsilon, then x minus a was less than these two. Limit as x approaches a of L. Now this picture obvious, but that's clearly a simple theorem or squeeze theorem when the function can't be controlled real easily. The function is slightly smaller, well, near the point A. So our situation is x approaches a of f of x. An example of if f of x is 1 over the graph of f of x gets close to 0. Consider numbers close to 0. The value of the function f as large as you would like. And this is the definition. X approaches a is equal to if for each one greater than 0 there is to be a large positive number going to make any difference. M, so I'm sorry, for each number m so that, again here, m positive number is larger than absolute x minus a. Okay, that's to say you can in any value m enough to the point A to A. The limit is set of function number m. M is being an absolute value but negative to make a difference. They're also greater than 0, so that less than m. And 0 is left A is less than here. Here the limit is by this. You notice that the limit, the statement of plus, this simply means x gets large, goes to A. For some functions, you're going inside a limit. For example, f of 1 over x looks like this. Limit as x approaches A on the right of f infinity. Let's remove the absolute value down. The limit of f of x is plus infinity. There is, so that f of x is when 0 is A is less than delta. Right? On the left, f of x, change this to 0 than A minus delta. And then it's infinity as x on the left, as x approaches A, as x approaches A on the right, approaches A on the left, infinity. Infinity, then it's going to be infinity. If it's infinity on the right, you find this delta here side, and this delta here, the smaller of the two, and then as x approaches A, it will be larger than m for the small, no matter whether you're on the absolute x by. Now I want to take a look at some example. Infinite limits, how to deal with them. Function is equals to plus 3 over minus 2. Limit x approaches 2 from minus 2 here of the limit and left. Okay. As the numerator in this function gets close, and the denominator gets from 2 from with 2. So the numerator gets close to 0, and large and positive limits the 2 from the right. From the left of this function, close to 5, the denominator 2, when you consider numbers and you take that negative number, the denominator will through negative values 5, and so the limit is going. If you were drawing the graph of this function, something like this. 2, an infinite limit, as you either the right or the left, large, and gets close to the vertical line through that point. It's called an asymptote. In this case here, this function line, x equals 2. On the right and the left, it approaches minus infinity. Half of this is the shape of 2. Let's consider g of x is 3 over 2 squared. Now, the limit as x approaches from the right of this function, well, as the numerator approaches 5 through positive values to be infinity from the right. It approaches 2 from the left, which is 5. The 0, where it is approaching 0 through consequently, the actual this function is going to, so the function f looks, its graph is here. G has 2 parts like this. As x approaches 2 from the right, the g of x gets close to the line. Both of these have x equals to asymptote. Let's look at another such example. Equal 2 minus x over 4 minus x. And now here we're interested in the point 4, the denominator here. We want to find the limit approaches 4 over 4 minus x from the right as in the left for 4 minus x. Well, as x, the numerator from the right, we consider numbers which are large, 4.1, the denominator. So the numerator approaches, the numerator is negative, the quotient is going to be positive, it is going to be equal. Half of this then, as we're near the point, is going to x equals 4. As x approaches 4 from the numerator approaches minus less than 4, however, so this is going to be, and so from the left, our limit of the numerator is going to get close to 0 through positive values. 4 from the left. Limits of, look at another function, g of equals to, here we'll be interested in the limit as x approaches 2 of x. The numerator here, the denominator is larger than 2. So we're going to have the number that's going to be negative, but it's going to be close to 0, so it's going to be very large. Negative, large, and so this limit is going to be minus. So this is what the function fg here looks like this. Right? To the left, the limit is 2 from the x over 2. The denominator, now we're approaching numbers which are less than 2, positive, we're going to have up limits. The positive values and the numerator. So that the quotient, this is what g looks like here, 2. One more example. Vertical asymptotes and limits are infinite. Equals squared over x. It's not going to be defined when x is 2. And so if we regress, when we get close to minus 4. What happens here? We want as x to the right of f of the denominator approaches 0 at positive values. Quantity x plus 4 and the quantity x minus positive. So the numerator 4 0 through positive values. The limit here is going to be infinite. Have an asymptote with this. How about the limit as x approaches 2 from the left? It's going to get close to 6, so it's going to be positive. But now on x minus 2 is going to be negative. It's going to approach 4. The numerator is going to approach 0 through negative. Limit is going to be minus infinity, and the graph's going to have to look something. How about the limit x approaches from the right of x? 4. X minus 2 is going to approach 16. So it's positive 16. Rate of minus 4 at minus 3. This is going to approach values, and so the limit minus infinity. So the graph looks something like this. And in front, 4 from the left. This is going to be negative as x4. And as from the left side of minus 5, this is going to be negative. This is going to approach 0. The numerator is going to approach, but this is going to be equal, and x equals, and I draw the graph.